All right, so we're going to this week off with Lab 4. So this is going to be a chance for us to kind of look a little bit more at some of the radiography stuff. So this is kind of part 2 of the radiography series of labs we're going to be doing. So transmission radiography is going to be a process of measuring and recording changes to some kind of beam that's coming in, resulting through passing through some sort of area of interest. So we kind of got some sort of X-ray source here. We're shooting beams into the area that we care about. So this is, say, the brain, and then some of the X-rays are going to get through to the other side, and we have some sort of detector over there. And so when we're looking at views for a radiographic setup, we got to have some kind of words we want to go ahead and define. So kind of an area of interest that we're looking at, or just kind of a slice of that, is going to be some n by n array of voxels. So voxels are going to kind of describe different segments of the brain that we're looking at. And for our purposes, we're going to be looking at a square area of them, so n by n. Total number of voxels we'll have then in each slice we care about is going to be little n squared, and we're going to call that big N. Each voxel has a width and height of 1 unit. So whatever that unit is, we're just going to call it 1 unit for now. Each of our views is going to be recording m pixels of data. So the pixels here are going to be what we divide each view into. So instead of just having one particular view, the view is going to be kind of split up into different segments. And so the width of each of these pixels is going to be known as the scale fact. Most of the time, we're not going to have to worry too much about scale fact. It'll be kind of intelligently chosen for us based on some geometric things. If scale fact is equal to 1, then the width of the pixel is the same as the width of the voxel. So in other words, these square areas that we're looking at in the slice of the region of interest, or the part of the brain, is going to have the same width then as the pixel if the scale fact is 1. We're often not going to have to worry too much about scale fact, though, except for one example. So here's kind of a view of what we're looking at then. We're looking at kind of each of these. This line here is kind of our detector. So this is where our view is coming from, and the detector is split up into these different pixels. And then here we have kind of a region of interest. So you see here there are 1, 2, 3, 4, 5, 1, 2, 3, 4. This isn't the whole thing. And these individual squares are voxels. And so what we're going to be doing is we're going to be setting up a matrix that looks at the percentage of each individual voxel along a certain pixel's beam path. So let's kind of take a look at an example then. So in this lab, we're going to be given kind of some specific scenarios of what the setup's going to look like. So we'll have a total number of voxels, which will tell you big N, which is how many of them there are, and little n, which is basically telling us how many wide and long we have in each direction. We're also going to have a total number of views. So in this case, we're only going to have a single view. So the view is the whole set of beam paths that we're using to look, and along each view is going to be a particular number of pixels. In this case, it's 2. So here we've got a beam path here and a beam path here. The scale fact, like I said, is not going to be that important. The reason it's chosen to be the square root of 2 this time is to make sure each of these is wide enough so that based on the angle we're coming in at, we can get as much of each of the voxels as we need to be able to see 100% of each of these. And then the angle that we're talking about when we're discussing the setup is going to be degrees clockwise from straight down. So in other words, if we go straight down, this is going to be our 0 degrees. And then as we go to get to something that is along here, and this is coming straight from the middle, when we come to here, we'll have traveled 45 degrees to get the center of this path right there. So when we're making our matrix, what we're going to do is we're going to look and make our entries be the percentage of each of the different voxels along each beam path. So we can kind of think of each row as being a different beam path for our views, and then each of the columns is the percentage of each of the different voxels along those beam paths. So as an example, when we look at beam path 1, note that the numbering is a little weird here. We go x1, x2, x3, x4. Along beam path 1, we have half of x1, so we put a half. The entirety of x2, so we put 1. None of x3 along this first beam path, so we put 0. And half of x4, so we put a half. Along the second beam path is half of x1, none of x2. The entirety of x3 shows up along the beam path, and half of x4 shows up along this beam path. So if we have some sort of input vector, our output is going to be this matrix times this particular x. So here, if we're saying that our input is this x of 10, 0, 5, 10, this is going to be the x1, x2, x3, and x4. And so we need to find a way of representing this as a vector in this case, R4. So here we'd be saying that the image of this, if we were putting it in here, would look like 10, 0, 5, 10. And so we'd have something like this. We go into this, and this is kind of what our setup vector looks like. Note that the entries of the matrix are percentages. They're not these individual values. So you don't want to put 10, 0, 5, and 10 in your matrix. They'll be in the vector you're looking at. And so as we go ahead and try to find the output, which we're going to be calling a radiograph, what we will do is we will take 1/2, 1, 0, 1/2, 1/2, 0, 1, 1/2, and multiplying it by 10, 0, 5, 10. And so when we do this, our first entry should become 10 times a half, so 5, plus 0, plus 0, plus 10 times a half, so 5. So 5 plus 5 should be 10. And our next entry should be, I made this way bigger than I needed to, 5, 0, 5 plus 0 plus 5 plus 5, so it should be 15. So just to double check that I know how to do math, if we put these matrices in our calculator, we have 2 rows and 4 columns, so we'd have 0.5, 1, 0, 0.5, and 0.5, 0, 1, 0.5. And our vector was 4 rows and 1 column, so 10, 0, 5, 10. If we take A times B, we get 10, 15. And so this is our output that we get from the computer when we go ahead and put this object in. Now note that in the real world, we're not often going to have what these individual masses are, right? We don't know what the actual values are of the masses within the brain, or these intensity levels. We're going to end up getting the outputs most of the time. So we'll have a video kind of in the future, or in a future lab, talking about how we'd kind of go and reverse engineer this process. But for today, what we're going to do is we're going to be making sure we can come up with the matrix, understand what the input looks like, and then figure out what the computer would be telling us our output would be. So let's go through maybe 2 more examples, just to kind of get you guys started and make sure you guys are understanding where things are coming from. All right, so what we're going to have is some sort of setup like this. Again, we're not going to worry too much about scale fact. And what we will do is we will go ahead and create an image in voxels. It's going to be a 2x2 image. And then remember, we're going to use x1, x2, x3, and x4 as our ordering. So we have 2x2. We're going to have our views are going to be having two beam paths along them, and we have two views, one at 45 degrees and one at 135 degrees. So again, if we're starting here at 0, 45 degrees, as we saw in our previous example, is going to come down along here. So we'll have beam path 1, beam path 2, and this is going to be at 45 degrees. And then our second view is going to be at 135 degrees. So we'd kind of take this and we'd continue. So this would be 90, and so 135 is going to end up here. So again, we'll draw. Then kind of note that if we take and follow along where beam path 1 is going to be, beam path 1 actually ends up here, and beam path 2 ends up over here, and so we have 135 degrees there. So if we look, kind of set up our views. So this would be sketching what our setup is going to look like for this. So as we go ahead and we create our matrix, we'll call it T. Each of these rows is going to correspond to a beam path, but from a different view. So these first two will be view 1, which was our 45 degrees, and these next two will correspond to view 2, which is 135 degrees up there. And then remember, each column is the percentage of the different voxels that we have, x1 through x4. And so when we look at view 1, this is the first beam path. We want to know the percentage of each of these different voxels that shows up. So half of x1 is showing up along this beam path, the entirety of x2, none of x3, and half of x4. So this should look similar to the matrix on the previous page. And then we look at this next beam path, x2, the entirety of x3, and half of x4. If you're feeling confident, I'd encourage you to take a minute to try to find these next two rows on your own by pausing the video, and then kind of coming back and making sure and verifying that you've got everything. Okay, came back, great. Now, we want to look first at beam path 1 from the second view. Remember, the beam path 1 is this one, and so none of x1 should show up. We should have half of x2, half of x3, and the entirety of x4. And then looking at our second beam path, we have all of x1, half of x2, half of x3, and none of x4. And so this should be the matrix we get. Now, this third step in these is going to be to check the code using code TomoMap. So TomoMap is a function that I've gotten from the people who created this lab as part of the image math program. And what you can do is you can go ahead and I'll show you, there's directions a little later in the lab about how to use TomoMap in order to write code that can tell you what this matrix should be, and this can help you check and verify. Now, the reason it's been so important to do x1, x2, x3, x4 is this is the numbering order that the TomoMap code uses. And so if you do x1, x2, x3, x4, it'll change your matrix a little bit, but it'll change it so that it doesn't look exactly like the TomoMap output. So if you create a matrix using x1, x2, x3, x4, as long as you're consistent, that should be fine. But know that when you double check with TomoMap later, you won't necessarily get the same thing. All right, so let's look at kind of one more example from the lab. I want to just check something on the next page very quickly. Yeah, okay. So there's a typo I get to correct on the next page, but we'll get to there when we get there. So suppose that we now have this as our setup. So what we want to do is we want to be able to look at the setup that we have. And then we want to be able to go ahead and create a the radiographs for these objects. So I'll do one of the objects in a second. But what we want to do is we'll set up our voxels, so we should have a 2x2 based on this. We'll have x1, x2, x3, and x4. Pretend that I drew my line a little bit straighter than that. And we're going to have two different views. A view at 0 degrees and a view at 90 degrees. And each of these views has 2 pixels. So we'll split it up like B1, B2. And remember, when we rotate, we need to take where these are into consideration. So that means B1 and B2 will be here. And their scale fac is 1, so they'll have the same width as the voxels. This is just a fun word to say, voxel. And so if I had drawn my line straight, everything should look great. And so this will be sketching the setup. And if we want to go ahead and calculate our matrix T, again, the first 2 rows should be using the first view and those beam paths, and the next 2 rows should be similarly, or kind of sort of that. On the second beam path, we have none of x1 or x2, but we do have the entire x3 and x4. So that's our first view. Our next view, we're going to be looking at B1 and B2. So remember where those are kind of in relation to where the rotation is. And so here we have x2 and x4 show up completely on the first beam path, but none of x3 or x4. So we should have 0, 1, 0, 1. And along our last beam path, we have x1 and x3, but none of x2 or x4. So this will be our T matrix. Now when we want to go ahead and find our radiograph, we first need to go ahead and take and convert the voxels we have into a vector that we can multiply by. And so remember, we're going 1, 2, 3, 4, so we should have 4, 6, 3, 1 as our vector. And so if I want T times X, that will be 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, times 4, 6, 3, 1. And so we could do this on our calculator, but what we should get for the first entry is 4 plus 6 plus 0 plus 0. So 4 plus 6 is 10. 0 plus 0 plus 3 plus 1 should be 3 plus 1 is 4. 0 plus 6 plus 0 plus 1, 6 plus 1 is 7. And 4 plus 0 plus 3 plus 0, 4 plus 3 is also 7. So this should be the first one, T sub X. So kind of for extra exercises and kind of for the lab, I recommend trying to find the image for Y using T sub X, and then kind of there are more examples as we go through more of the labs. So here we have another view you can set up. You can try to find the radiographs from those first 2 X and Y's using this if you'd want. There's kind of some long steps here, a little bit of a clarification. For this long example on how to use TomoMap, you're using the n, the little m, the theta, which is the degrees, and then the scale fac that gets put in. So if you're just putting in this information. Here the example it talks about is if you have n is 4 and m is 4, the angles are 0, 20, and 90. Here we should have 0, and instead of 22.5, that should say 20, 90, and then a scale fac of 1, you'd put in 1. And if you want to write square root of 2, it's SQRT2. This extra example here, again, if you want to tackle this in the discussion boards, I'm more than happy to see you try it. Note here that the scale fac is 1. So scale fac is 1 works when we have things like 0 degrees or 90 degrees or 180 degrees, but it cuts things off when we're looking at 45 degrees. So this one you can definitely give an attempt. Maybe try to figure out what the geometry will actually end up making the output be. But then when you look at TomoMap, note that, you know, you have things cut off. So TomoMap can help you see exactly what happens at that point. And then kind of the last part of this is consider if you are looking at those images from before. I want to know what the radiographs are, and you can say this in the discussion boards, of taking this object and multiplying it by 3 first and then putting it through the transformation, or multiplying this object by 0.5 and then putting it through the transformation, or combining these after you've multiplied them by their respective numbers and then putting them through the transformation, and see if you notice anything. And if you kind of notice something, it may or may not be related. Note it is related to some of the things we have kind of coming up in this week's video. So definitely play around with this a little bit, and then, you know, move on to looking at the notes, and I will see you on the discussion boards.